Hello everyone, I am Mosam Pandya, your course instructor for measurement in industries, and we will continue with the previous session from the semiconductor types of strain gauge that we stopped in the last session, and we will be looking into fiber optic type of strain gauge also today. So let us have recap very quickly what we did in the last session, that is wire wound resistive strain gauge, bonded and unbonded, and the metal foil resistive strain gauge, and this was the schematics and some pictures we saw with the understanding of the strain gauge configurations. And where we stopped last time, so this was the semiconductor type strain gauge that I talked little bit about that, and the one very crucial word, piezoresistivity, where semiconductor type of material, when they are stressed or their stress is applied, then their resistivity will be changed, and this typical characteristic is known as piezoresistivity, and this will be utilized to sense the stresses, specifically dynamic kind of measurement. See, in the previous all strategies we saw that was a static measurement where a simple change of the resistance was done because of the application of stress. Now what if dynamic or varying kind of stress? So this is the better strategy, and in addition to that we will see the optical type of strain gauge that is also very useful when we talk about the dynamic changes. And this was the configuration or schematic that we saw with the coloring nomenclature that we have used here: p-type silicon, n-type silicon, and polyimide film, basically bakelite plastic, the p in gold wire, aluminum, etc. So see here, this is the basic configuration, where once again this is the two-dimensional version of the semiconductor strain gauge, where semiconductor material and gold wire, because gold has a very good gauge factor with respect to the stress measurement and strain measurement idea, and so that's why it is used for connections to the outer terminal. And these semiconductors are so minute, they are very small in the size. As I explained in the previous session, that metal foil was so small that it can be fixed on your nail also. So what is the basic process? A rectangular filament made as a wafer, like this, a semiconductor wafer of say approximately 150 micrometer, from it may be silicon, it may be germanium. Okay, and keep in mind, these are the pure semiconductor, silicon and germanium crystals, and we add boron for the deposition, for doping purpose. And once again, plastic or stainless steel, here we are using plastic, I say polyimide or bakelite material as a backing. And once again, leads are made up of gold drawn out from the sensing element. And types, basically two types. As we always talk about semiconductor, we'll be having two choices, p-type and n-type usually. So negative or n-type semiconductor strain gauge, positive or p-type semiconductor strain gauge. So if we talk about say n-type, that there it's a negative temperature coefficient kind of thing. We can analogy make an analogy here. Resistance strain gauge of a negative type will decrease the resistance when tensile strain is applied. Here we talk about with respect to the tensile strain reference. Let me go back a little bit. And positive type of strain gauge, where tensile strain is applied and resistance will increase, and that is basically depending upon the type of semiconductor that we are choosing. So here you see the actual scale of the work, and I have shown you the specimens, actual specimens when it is actually prepared. Here you can see the size of semiconductor sensitive resistor, where it is fixed, even it is smaller than the connecting wires and leads. Okay, so you please observe this very carefully, how gold wire is connected to the semiconductive sensitive resistor and fixed on the polyimide film. So let us try to establish step-by-step formation that you can draw in the examination, or you can write down those points also that we saw in the previous slides. So once again, let us remember the colors that we are using for the layers in the semiconductor. So very first of all, let us take a silicon wafer of say 150 micrometer thickness or kind of thing. And boron implementation, boron here, that's a P-type of semiconductor doping. It is being doped in the silicon wafer. Then aluminum deposition is done for making a layer, and then we will be making a pattern of aluminum. Then silicon pattern is generated. The boron implemented part is matched with aluminum patterning, and outside etching is done, polishing backside and etching backside. Our major concentration is of step number 2, 3, 4 and 5. See, etching process and polishing, these are actually some mechanical process, but here we have to see how actually one semiconductor layer is prepared. This is very meticulous and very micro level process, and how finally our semiconductor strain gauge will look like. And I had shown you the actual version. So here we say piezo resistor or say piezo resistivity, what we are using, and now it is ready for us, and we can use it for some measurement of the stress and strain. So what are the advantages? Very small size, high gauge factor. I hope you remember gauge factor. Then low hysteresis. Then a very good frequency response that comforts with the AC measurement. See, in the previous sessions we saw that Western Ridge was used, and we were using a DC supply of 5 to 10 volts. Here you can use it with the AC measurement. And disadvantage is temperature sensitivity. As we know, the material is very small in size, and semiconductors are temperature sensitive material, and the non-linear characteristics. But anyways, this can be compensated by adding another strain gauge in series or parallel, and we can overcome these disadvantages. Next is fiber optic strain gauge. Which is actually known as FOS or FBGS. The optical strain gauge is actually designed differently than the conventional fiber optic strain gauge. It is not like that we took one light and we took one pipe and we just measuring the strain oscillation, but it has little bit different pattern. And the one very much important word is Bragg frequency or Bragg grating. Fiber Bragg grating. You remember it is FBG, and this will create interference. Like it is like you can say we have. Oh, okay, so it can be. Let me show you this. So this kind of 1, 2, 3, 4, 5. This grating here, it is created inside the fiber optic space that we are using to sense the stress and strain. So this kind of grating is created, and extremely long glass cylinder, very thin, and it will behave like a window through the cylindrical fiber is getting into that, and a light is passing, and now that light will be reflected or passed through certain wavelength. We are talking about wavelength, and that reflection will decide the amount of strain, because it will be disturbed by, or it will be changed by the presence of strain. And as I said, FBG, this Bragg grating will change its shape due to the application of strain. And say for example, if it is in tension, then it will experience positive strain, and vice versa. When it is compressed, the gap shortens and strain is negative. Let us see how actually it looks like. The broadband light is inserted, and you see the application of external strain, this big arrow, and here the grating is now RW. RW is reflected wavelength, and reflected light from the core. See, this is transmitted light, say in the direction of these arrows, and the different colors in the arrow is looking like rainbow, but it's not rainbow. It is the different frequencies of the light, and out of that you here see the green color is being reflected back. So before application of tension and after application of tension, that is reflected. It has got difference, and this blue one is that was before and after. And here in the FPG2, that is, we do not observe right now change, because strain is applied here on the first specimen. Here FBG1 you observe where strain is applied, here no strain is applied, so this difference will be observed, and here epsilon strain and the time. So basically when we talk about the time element, our measurement becomes dynamic. So it is very much useful for the dynamic. So you should remember that somebody asked you somewhere in the interview or somewhere in MCQ, which strategy can be utilized for making dynamic measurement of the strain, then you should use fiber optic strain gauge. This is one of the very popular strategy being used nowadays in sophisticated measurements. And the actual strain gauge will be looking like this vertical portion you see here, and the grating I have shown here, and that grating is meshed with this fiber optic, which will actually change. This is input light. I am showing once again with respect to lambda. Lambda is actually related to the wavelength. Wavelength, it is related to the time. So reflected light at the Bragg wavelength. So this part is reflected, and that remaining part will not be reflected. So this gap you can observe here, and this is in turn will be giving you the strain presence, and this intensity will give you the actually amount of the strain. Okay, so dynamically it can vary across the axis. And once again the practically implementation of this optical strain gauge, and here you see the first diagram in the upper portion of the screen. This column beam, this is the beam, this violet color we indicate as a beam, and as and when the column beam is going under stressed position, say tension or compression, that will actually be sensed by this fiber optical with the FBG arrangement, and will be giving you the particulars. And the entire practical arrangement is shown here. This limit disc fixtures are there, and metal shell are there, and see, this is very sensitive area, so it should be having very robust kind of cover. So the protection is required, and within this the optical fiber is kept for the measurement. Now with this we will be going with one more animation. We will try to understand how actually it works, FOS or FB. Okay, so we see here FBG concept and how actually it looks like, and this is the area where grating is applied. The magnified view you can see typically say 8 mm and the grating space, and here you can see cladding, core and coating. So these are the three layers of the cable, and as incident spectrum light is passing through, under no stress there will be no change, and a particular reflected spectrum is going back. Now strain sensing, say tension or compression. Now you observe the position of the reflected spectrum which is moving with respect to application of strain. Very well you can observe here. And strain with respect to time, you see dynamic measurement is possible here. I am repeating the word dynamic measurement, so you have to be very clear when to use static and dynamic. And another parameter that you can use, say actually we are talking about stress and strain, but we have temperature sensing element can be here. We can make it for the temperature measurement also, and the reflection of the particular wavelength can be termed in terms of temperature with respect to time, say dynamic measurement. So this is what I tried to add you here. And you see the pattern of the variation in the temperature, and with respect to time how you get the readings or results. Hence we saw the entire procedure of FOS or FPGAs, and in today's session we tried to cover semiconductor type of strain gauge and theoretically FOS or FPGAs. These are the very important topics as per your exam point of view as well. See, our motive is to learn and to understand the instrumentation strategies for the industries, but as it comes to the examination, you should remember the certain ideas and concept. So I hope the two topics are clear to you. Still, in case if you have any doubt, you can write down to this email, and we will be joining you in the next session of the measurement in industry with some more few topics. Thank you so much.